Hi everyone. So today we'll be talking about molarity and dilutions. Molarity describes how concentrated a solution is. If you have pure water, then you add a little bit of salt to it, you might make a dilute solution. There might not be a lot of moles of solute, that thing dissolved in the solvent water. But if you add a lot of salt to that water, then you might have a fairly concentrated solution. It would have a high molarity because it would have a high number of moles of solute per liter of solution. So we can use this equation to describe molarity, but also to, or concentration, but also we can use it to prepare solutions as well. So here's a question. How can you prepare 500 milliliters of a 0.2 molar calcium chloride solution? Generally, if you want to prepare a fairly precise molarity of solution, you want to prepare it with a precise volume, and you can do that using a volumetric flask. The volumetric flask is kind of wide throughout most of it, but right near the top it's kind of thin. And there's a line there. So for a 500 milliliter volumetric flask, at that line, if you fill right to that, you will fill 500 milliliters of solution. Okay, so if you want to make 500 mils of solution, maybe you'll use a 500 ml volumetric flask, and you'll add some calcium chloride to it, and then fill to the 500 ml line with some distilled water. So really now the question is, how many grams of calcium chloride do you need? Well, you can know that if you know the number of moles of calcium chloride you need, and we do know that we want to prepare 500 milliliters or 0.5 liters, and we also know we want its molarity to be 0.20 molar, so knowing these things we could find all of these. So you can take the molarity is equal to mole over liters equation and rearrange it to get moles is equal to molarity times liters. Plug in for molarity was 0.20 molar, and because we wanted to prepare 500 milliliters, we could divide that by 1,000 to get 0.5000 liters of solution. Multiplying those, we get the number of moles of calcium chloride that we would need to prepare that solution. But why is this calcium chloride, and why not CaCl? Well, calcium chloride would have ions of calcium, which are Ca2+, and ions of chloride, Cl-, and the only way that those can combine together to give a reasonable compound which balances the charge is to crisscross. That's CaCl2. Now there's two chlorides, two -1 charges there to balance out the one calcium, the one +2 charge. So the positive and the negative charge cancel. All right, so we know the number of moles of calcium chloride that we need to prepare the solution. Now we can't measure out a certain number of moles though. Our scales don't measure moles, they measure grams, mass. So convert your moles of calcium chloride into mass of calcium chloride by using the molar mass. And so you can find that to prepare the solution, you want to have 1.11 grams of calcium chloride and then add water to it until you get to the 500 ml line. If you had added 500 milliliters of water to that number of grams of calcium chloride, you would get more than 500 milliliters of solution, and hence having the same amount of solute but a larger volume, it would be a little bit more dilute than you would hope for. That's why we're careful to prepare precisely 500 mils by using that volumetric flask. Okay, kind of a side question here. Let's say we had that 0.20 molar calcium chloride solution. What would be the molarity of chloride within that solution? Well, when ionic compounds dissolve in water, they break off into separate ions that float around solvated by water. For every calcium chloride, there's one calcium and two chlorides. So if we want to know the molarity of chloride there, it should be twice the molarity of calcium chloride. There's two chlorides per calcium chloride. So we can solve for that mathematically by saying, if we have 0.20 molar, it's 0.200 moles per 1 liter of calcium chloride. And per 1 mole of calcium chloride, there's 2 moles of chloride. We can see that number right there, or in our drawing. And so there's twice as many moles of chloride per calcium chloride, so there's twice the molarity of chloride as well. All right, kind of a different topic. Dilutions. So you might keep in the back stockroom a certain molarity of solution. So like I have quite a bit of 1.0 molar sodium hydroxide. But sometimes I might want some 0.15 molar sodium hydroxide or 0.17 molar sodium hydroxide. I can't keep every one of those solutions available. So what I do is I keep a concentrated version of sodium hydroxide, and then anytime I need a more dilute solution, I can just get some of that concentrated solution and add water to it to make a dilute solution. If I want to make 1 liter of 0.10 molar sodium hydroxide, and all I have available in the stockroom is 1.0 molar sodium hydroxide, I can add water to some of that to make a larger volume. See, we have a fairly concentrated solution. There's a lot of dots per unit of volume here. But we want to make a more dilute solution. Same number of dots, but in a much larger volume. And we can get that by spreading those solute particles out by adding more water. Kind of our big question on how to prepare this solution would be, what volume of that original concentrated solution should we start with to make 1 liter of 0.1 molar sodium hydroxide? Okay, and so to solve for any dilution problem, when you start with a certain volume of solution, you want to make a different volumes of solution. To solve any dilution problem, you want to use this equation. M1V1 is equal to M2V2. It derives from the fact that if you have some amount of solute, like here these 10 dots, if you surround that with more water, you'll still have just as much solute as before. The number of moles of solute at the beginning and at the end are the same. We also know that molarity is equal to moles over liters. So you can replace that moles with molarity times liters. Moles is molarity times liters. And so replace moles at the beginning with molarity at the beginning times the volume at the beginning, M1 and V1. And then replace moles at the end with molarity at the end times volume at the end, M2, V2. So you'll use this equation quite a bit. And again, we're trying to find what is the volume of this concentrated 1.0 molar solution that we need to prepare this other solution. So we want to know the initial volume before dilution. We want to know the value of V1. So we can take that equation and manipulate it by dividing both sides by M1, and we get V1 is equal to M2 V2 over M1. Then we can start plugging in. You can just plug in the molarity of that dilute solution, M2, and then the volume of that final or that dilute solution, 1.00 liters, and then the molarity of the initial M1 solution, that was 1.0 molar. Okay, and so molarity cancels out. We're left only with liters, and so we'll need 0.100 liters, or multiply by 1,000, 100 milliliters of that more concentrated solution to prepare 1,000 milliliters of the less concentrated solution.